This is our PowerPoint on background radiation. Again, a very quick one. So, background radiation is something that we can't do anything about. It's hitting our bodies all the time, from above and below, and you can kind of categorize these as natural or artificial. So natural sources from food and drink, or cosmic rays from space, nothing at all you can do about it. You can see a large chunk on this pie chart is radon gas from the ground. What happens there is, in rocks like granite, and there's a lot of that in places like Devon and Cornwall and Scotland, you get uranium. So you've got uranium in rocks, and this decays into other radioactive substances like radon gas. And what can happen is that can seep up into people's houses, where it builds up and people can breathe it in. So people are breathing in this radioactive gas. The effect of this is to cause ionization and damage to the soft tissue in your lungs. And over time, this is going to increase the chances of you getting cancer, or it could even kill you. Artificial sources, sort of man-made sources, nuclear power and weapons tests, even Chernobyl, when Chernobyl in Russia went into meltdown, that increased the amount of radioactivity in the world. Medical sources, that's by far the largest chunk there on that pie chart. That's the biggest amount that you're going to get. That's the biggest source of radiation. And that's things like using radioisotopes for diagnosis or treatment in cancer treatments and things like that. So our background radiation comes from artificial sources, and it comes from natural sources. Let's go back and look at an atom. Now, if you watched my video on how to draw an atom, you'll remember that the centre part, the nucleus of an atom, is positively charged. It's got a proton and it's got a neutron. The neutron, as the name sort of suggests, neutral, has no charge at all. So the only other thing in the nucleus is the proton, which has a plus charge. The negative charge in an atom is in the electrons, which go around the outside. So, and the rule is, in an atom, all atoms on the periodic table are neutrally charged, because they've got the same number of protons as they have electrons. So, for example, carbon. Carbon has got 6 protons in its nucleus, so it's got an overall charge of +6. It's also got 6 electrons going around the outside, so that's 6 negative charges. 6 pluses cancel out 6 minuses, and the overall charge of the whole atom is neutral. But what would happen if we were to get rid of one of those electrons, one of those 6 electrons? And now we've still got the 6 pluses in the centre, but now we've only got 5 negatives. 5 of those negatives will cancel out 5 of those positives, and we're left with 1 remaining positive. Now, that's called ionization, and this is worth taking note of. Ionization is when an atom, a neutrally charged atom, becomes charged, and this is usually through loss of an electron. So our carbon now has a +1 charge, and it's called an ion. So in future, when I refer to ionization, that's what I mean. Our atom picks up a charge. So there we are, there's a picture of ionization happening. We've got our ionizing particle, this could be an alpha particle or something like that, smashing into an atom, knocking an electron off. Now that electron is free to go off into the distance, and if there's anything positively charged around, it may move towards that. The atom itself has now got an overall plus charge, and if you put a negative terminal, a cathode, near it, it would move to that. You can detect radiation, these sort of what we call radiation events, using something called a GM tube or a Geiger-Müller tube. In the movies, you often hear it referred to as a Geiger counter. And the way a Geiger counter works is it's this tube with a positively charged anode going through the middle, and the outside is negatively charged. The casing is negatively charged, and it's got some sort of helium or argon or neon or some inert gas inside. And when a radioactive particle goes through the tube, and in class what you'll see is we'll take a source and we'll fire it through that mica window, so that the actual radioactive particles will be firing through the mica window and into that cylinder. And what happens is they leave a trail of ionized particles bashing the electrons off of those atoms. Now the electrons are negative, so they'll go to that blue positive charge, and the rest of the atom that had the electron knocked off is positive. So that will move to the casing, it will hit the casing, and that will send a signal, a little pulse, through the wire, and that's registered usually as a beep. So that's why you hear those beeps on the Geiger counter. And if you don't have to put a source up to it, if you just hold it up in the air, it will beep. Why? Because there is background radiation all around us and there's nothing we can do about it. Let's move on to how some uses of radiation. There's two to look at. The first one is how a smoke detector works. A smoke detector has a radioactive source and it has an alpha source. It's called usually americium. And it fires alpha particles out through this little hole in this negative terminal, and these alpha particles will ionize the air. So oxygen and carbon dioxide and nitrogen, the alpha particles will smash into them, knock an electron off, and the electron will move its way up to the positive plate, and the positive ion left behind will move itself down to the negative plate. Now this constant flow of negative electrons hitting the positive plate kind of completes the circuit and lets a weak current continue to flow. Now what happens if there's a fire? You get smoke. The smoke particles get in the way of the alpha particles, so the alpha particles don't get to cause much ionization. Hardly any electrons now are making their way to the positive terminal. The current drops drastically. This is sensed and the alarm goes off. So just a bit of smoke is enough to stop these alpha particles, because if you remember, they're not very penetrating. And that's how a smoke detector works. If we move on, the second one, if you have an underground gas pipe and there's a blockage or a leak, what you can do is you can use a very small amount of radioisotope gas into this pipe, and the detector tracks the progress of the radioisotope down the tube, down the pipe. And when you suddenly get this increase in activity detected, you found the blockage or the leak, and you know exactly where it is. It saves you digging the whole area up. So it's kind of a diagnostic tool, really. So there we are, very quick one. So that was background radiation and two uses of radioactive sources. Once again, we have some questions. So pause the video, have a go, and good luck.